For our last part of Chapter 7, we are going to look at ions and electron configurations and a little bit of properties for that. So we'll start with anions. They're pretty easy. So we'll go negative first, anions. All right, so we've already kind of done a little bit of this, but essentially when we're looking at anions, we add electrons. So those electrons are added just straight to the configuration. Add electrons to valence shell. And then just write out the configuration. Okay, so again, let's look at oxygen. Okay, so normal neutral oxygen is 1s2, 2s2, 2p4. So what this chapter tries to sort of bring together is that in chapter 2, we learned that oxygen forms oxide, which is O2 minus. But if we look at the configuration, it's just 2 away from having a full N equals 2 shell. So it kind of makes sense that it would want to form or have a configuration where it's 1s2, 2s2, and instead of 2p4, to form 2p6. Okay, to go from here to here required us adding 2 electrons. So this is O2 minus. Okay, so anions will gain electrons to fill the outermost p shell. Okay, so that's true for all of them. Nitride, oxide, sulfide, bromide, all of those. Your configuration, just filling up this last p to get the 2p6, or excuse me, the p6, and then however many electrons it takes to do that gives us our charge of our ion. Okay, so we saw some simple examples of cations. So cations will lose electrons. Okay, so if it's representative, so if it's in the group A's, we tend to form a noble gas. Okay, so for example, we saw, all the things that were isoelectronic with argon. But for example, we could look at magnesium. So magnesium, 1s2, 2s2, 2p6, and 3s2. Okay, to get the most sort of stable shell, since the 3s doesn't really have very many electrons in there. In terms of energy, it takes less to lose these than to try to gain and fill that outer shell to become 3p6. So much less energy to just lose. So to just sort of knock those out, we would have Mg 2 plus in that case to knock those guys out, with the configuration of 1s2, 2s2, and 2p6. Okay, so that's a lot of what our representative elements will do. Okay, so now let's look a little bit at transition metals. So this is where it gets a little bit interesting. So let's look, again, they all form cations. So they still lose electrons. Lose electrons, but it's not quite as predictable. So lose electrons for our transition. Not quite as predictable. So we'll see a few that are, and then some that maybe not totally obvious. Okay, so one of them that's nice is iron. So let's look at iron. Okay, so iron is argon. Okay, after we fill argon, we go 4s2, and then we have 3d6. This is the filling order. Okay, so this is important. We are now looking at removing electrons or creating cations. So we want to have this in energy order. So the electrons that are ionized first are the ones at lower energy. So if we put this in energy order, we still have the argon, but now we're going to swap. We're going to have 3d6, 4s2. This is for energy. All right, so let's look at the configuration, or excuse me, the orbital diagram for this. Okay, so at lower energy, we have our D, so 3D, and slightly higher, we have 4s. So we have 4s2, so 1, 2, and 1, 2, 3, 4, 5, and 6. Okay, so iron forms two cations. So we have Fe2+. Okay, so to form Fe2+, let's take a look. What two electrons would we lose? Again, the highest energy electrons. So if we look at our energy order, it's these two S's. So these are the first two electrons lost. So highest energy, bam. So Fe2+ is argon 3d6. Okay, where those two highest energy electrons are lost. Okay, so iron also forms Fe3+. Okay, so Fe3+, still the core there of argon. But let's take a look now at what electron now could we, possibly lose. All right, if we take a look, the next highest energy here is going to be our spin down. So spin down would be the next one we'd lose. So to form a +3 charge, we would lose the S's first, and then that spin down electron at higher energy. So Fe3+ is argon 3d5. Okay, so higher energy electrons lost first, and then you start losing the D electrons. Okay, so if you look at the periodic table, so this one is a nice one, which I requisitioned from the lab, has a lot of oxidation states on here. So for example, you see a lot of 2s. So 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, so on and so forth. So 2 is a very common oxidation state for a lot of transition metals, and that's because these are the highest energy. So it's pretty easy to kick these off. Then to form something like a +3 or a +4 or a +5 or even a +6, then you're starting to lose these D electrons here. So the first two always lost are these ones here, and again, then you start losing some of the D electrons here. Okay, so let's talk about one of our exceptions, or one of the things we memorized as being type 1. So from the periodic table, we memorized that silver is a type 1 cation and it forms Ag+. So let's take a look at why that is. Okay, so silver, the configuration is krypton 5s2 4d9, which is predicted, but it does fall in the family where it can fill the D subshell by taking one of these. So the actual is krypton 5s1 4d10. So this is the actual. And then we have, of course, krypton 4d10 and 5s1, which is energy. Okay, so if we look at what silver has done here, it's filled its D, which we talked about it now being kind of considered core. So by doing this, we've now taken our core and extended it out. So that's core. So really our only valence electron is that 5s. So our valence configuration for silver looks like this. We have a 5s electron spin up all by itself in its own shell here. Okay, so to form silver Ag+, this electron right here is lost. So Ag+ is just krypton 4d10, okay, where that S electron is the one that's lost. Okay, so that's how the transition metals work. Again, we lose the S electrons first. They are a little bit higher in energy. Okay, so There's other ones on the periodic table that you could kind of go through and practice with. Like, for example, maybe talk about why, another one we talked about, why does zinc form a +2 charge and only a +2 charge? Another one you can kind of look at. I also do like to do one of these sort of metals here. So let's take a look at tin before we move on. Let's take a look at one of these other metals, like I said, tin. Okay, so SN. So let's look at our configuration for tin. All right, so tin is here. Okay, so our previous noble gas is krypton. So we have krypton, then we have 5s2, then we have 4d10. Okay, so that brings us here, and then we have 1, 2 to get to 10 here, so we have 5p2. So that's our filling order. Let's put it in order of energy. So we have krypton. Okay, so this is filled, so we're just going to put it back over here. 4d10. Then the S is lowest, and then the P. Okay, so right here, those ones there are core. So when we talked about ionization energy, again, we did discuss how it takes a tremendous amount of energy to remove these. So our valence electrons are right here. So we have the 5s, and then we have 1, 2, 3, 5p. So 1, 2, 3, and 4. Okay, so tin does fall into the group 4. So here, we learned that carbon can form an anion as carbide. But this one here, these ones down here, why we have some that are anions and some that are metals and are more like cations, it's just purely due to the size of the atom. Once you get so many shells and so many electrons, it's more energetically favorable to lose electrons to reduce the size of the atom. So that's why we have this zigzag line here. It's purely, again, due to size. Okay, so tin, a metal, loses electrons. Okay, so a lot of times it's like an all or nothing thing. So for example, it wouldn't be very energetically favorable to just lose one. Then you'd have one single electron in an entire subshell all by itself. So the first thing would be to lose both of those. So tin does form SN2+, so that would be krypton, 4d10, which again is our core, and we are going to lose the p electrons and have 5s2. Okay, so now these are essentially gone right here. So now if we look, we can't really, again, touch those, but we do have now these two electrons hanging out all by themselves in a giant, big, empty shell. So it doesn't take very much energy then to remove those and form SN4+, where those two and those two are removed, and then you result in krypton 4d10. Okay, so that's how these work here also. So that's why we get these configurations here. So again, even though it still kind of falls here, the oxidation states of +2 and +4, again, we can explain based off of its electron configuration and orbital diagram. But again, something up here, more like carbon, tends to want to gain to fill. And again, this is sort of the energy dividing line where gaining electrons is more favorable and losing electrons is more favorable down here. Okay, so that's how those work. So our last and final topic in this chapter is called Electron Affinity. So electron affinity. Okay, so this is energy of adding an electron to an atom. Okay, so let's look at how this works. So same sort of principle, atom in the gas phase. So again, all the energy measured is directly related to adding that electron. Okay, so let's say we have atomic chlorine. We want to add an electron, then we would get Cl minus, again, gas phase. Okay, so the energy associated with this, delta E, equals negative 349 kilojoules per mole. Okay, so this, again, adding an electron to an atom, again, in the gas phase, so all energy measured is directly the result of adding that electron. Okay, so a couple of things to note. For the most part, free electrons are generally higher in energy than being bound to an atom. So most of the electron affinities are all negative. Most of them. We'll talk about exceptions, and they'll be kind of ones that you would probably guess would be exceptions. So again, most of the time, this is an exothermic process because free electrons are higher in energy. Okay, so the last chart we're going to see is the electron affinity chart. Okay, so change in energy when an electron is added to a neutral atom. Okay, so again, for the most part, lots of negatives. So even something like lithium that we are used to forming lithium plus, even things like this have smaller but still negative electron affinities. Beryllium and magnesium, these ones have positive. Okay, so we'll kind of talk about that in a second. We get over here, group 3, 4, 5. Most of these are negative. Nitrogen is not. And then probably not shocking, but all of the noble gases also are positive. So in a positive case, when again it's greater than 0 or you have a positive electron affinity, that's because that atom already has a pretty stable arrangement of electrons. You're taking a stable arrangement of electrons and then trying to force another electron on there. Okay, so let's explain nitrogen, beryllium, and neon having positives. So that takes care of, this, this, and this are 3 major exceptions here. Okay, so get back to our sheet of paper, get our light. Okay, so our first one, oh, that's a little, sorry. Camera gets angry at me sometimes. All right, so our first one, it said to explain, let's explain beryllium. Okay, so we are going to look at why beryllium would possibly have a positive electron configuration, or excuse me, a positive electron affinity. So let's start with the electron configuration. So beryllium is 1s2 and then 2s2. Okay, so if an electron is added, so if we did Be gas plus electron to form Be minus gas, that electron is going to go into the 2p. Okay, so kind of full subshell. Putting an electron into the 2p requires a little bit more energy than having the free electron by itself. So we would have a positive delta H for this one. Because we're essentially filling up or putting an electron into another p orbital. Okay, so that's why it's positive for both Be and Mg, because you would be putting, like I said, an electron into kind of a new subshell. And recall that S and P are kind of higher in difference in energy. Okay, so it's not like S and D. That energy gap, sorry, we'll get my lighting. The energy gap between, say, the 2s and all the way up here at the 2p is quite large. So it takes a lot of energy to put an electron up here. Okay, so the same thing with the 3s and 3p, why magnesium is greater than 0. These are slightly negative because now for the 4, n equals 4 and n equals 5, those are a lot closer together because your shells start to get really closer together. So that's why it goes back to negative there. Okay, so that was our first sort of exception we saw there. The next one that's maybe a little surprising is nitrogen. So nitrogen is 1s2, 2s2, 2p3. So one of the things we did talk about, so I'm just going to go valence, 2s and then 2p. So one of the things we did talk about in chapter 6 was this is a pretty stable electron arrangement of electrons. Not as stable as a noble gas, but having your subshell filled with one electron, all of them spin up, nothing being paired, is pretty stable. Okay, so now you're talking to add an electron. So to go from, again, N gas plus that electron to go N minus gas, that electron that we would add would be this one. So then you're going to have to take something that's already pretty stable, put in one electron spin down, and pair it. Okay, so that's why this one has a positive delta H. So nitrogen's the only one. As they get larger, so when we go to the 3p and the 4p and the 5p, again, since those are farther away from the nucleus of the atom, it becomes energetically more doable than the really small nitrogen. Okay, so the last one is essentially all of our noble gases. So we'll take, for example, neon. So 1s2, 2s2, 2p6. So for neon gas plus electron to go to neon minus gas. You probably guessed it. That electron, which I've kind of done in red here. So this electron would 2s, 2p. Okay, so neon has the S and the P. So if we're going to add an electron, where is this electron going to go? You probably guessed it. Brand new shell opened up just for that one electron we're adding. Okay, so that's why these ones have, our noble gases have positive delta H, because now you're putting an electron into a whole new shell of an atom, which does take quite a bit of energy to do. Okay, so again, for the most part, adding electrons to an atom is an exothermic process, except for a few of our exceptions here. And you can kind of, again, one last thing kind of leaving us with this. Different elements that kind of are really, really close to a noble gas configuration. For example, like our halogens. All of those are pretty large and negative because it's taking that configuration for like fluorine, chlorine, bromine, iodine, and it's filling the shell. So that releases a ton of energy. That's incredibly stable. Gaining just one electron for, say, oxygen, sulfur, selenium, tellurium, energetically favorable, but again, we don't get that huge, large numbers we see here, simply because these ones are actually completing their outermost shell to become the noble gas configuration. Okay, so kind of as you would guess, looks like electron affinity for the most part is a little bit larger this way, except for, our exceptions. And definitely smaller this way. And electron affinity seems to be a little bit higher towards the top. But again, not always. We see here that these ones are kind of mixed up a little bit here. So not a super duper trend, but for the most part, your things that traditionally form anions are more comfortable or okay with taking on extra electrons. So these are larger negative values. Things that typically don't really want to take in extra electrons, still for the most part negative, but much, much smaller in magnitude. Okay, so that's it for chapter 7. So go back through, read, review, and do the homework.